Hey everybody, I just wanted to spend a little bit of time going over Lab 12, the Grignard reaction, and what's expected of you in the digital lab. So you'll see this video explanation, that's what you're listening to right now. And then here is the directions that you would normally do if you were going to be doing this in the lab. So you go through this, and now I will tell you that this particular experiment is really finicky. It's one of the hardest that you do in the lab. So much so that I usually tell students that that organic chemists get paid to purify stuff mainly, except for this lab where you're getting paid to actually do a very careful reaction. The main reason why you have to be very careful is because the intermediates in the reaction are not stable in water, okay? And they can also react with carbon dioxide and oxygen and things like that. But so looking at the mechanism, and it's a four-step mechanism here, or at least that's the proposed mechanism, I want you to identify what would happen if the reaction was exposed to water at between step 1 and 2. Okay, how does water affect the reaction? And then the same thing with excess carbon dioxide. Okay, and so that's to get you in the mindset of how finicky organometallic, specifically Grignard reactions can be. Okay, and of course we need some physical constants, you need masses and density, and then just like in other labs, I'm going to want you to calculate the amount of starting material you're going to need. And for the starting material, that's going to be magnesium N-butyl bromide, which is also called 1-bromobutane. That's another, that's a synonym for that. N-butyl bromide is kind of the common name for it. And then ethyl acetate. And then you want to make 14 grams of product. Just be careful because there is some stoichiometry you have to worry about here in these reactions. Okay, I'll highlight it right here. Okay, so just be careful. Okay, so you're going to show your work, and then that's all the pre-lab or the have to do during lab questions. And then afterwards, you're going to take this and you're going to do a characterization. And so, you're going to use the characterization that I provided to identify the product. So we have some yield numbers and index of refraction corrected for 20 degrees Celsius. Now, here's the IR. Note that the IR here is traditional, except that it's flipped. So you were used to seeing kind of the mirror image along this axis where this would come down and then these peaks, so the peaks would come down. Here, only recently have they gotten in the habit of trying to make IRs and the peaks go up. So it's not as common, but it's the same thing. So I want you to decide if this IR is of 5-methyl-5-nonanol or if it's of something else. Same thing with the C13 spectrum. Here's the carbon 13, carbon NMR. And okay, you're going to see here, the one thing that I will say is that it's hard to tell, but I'm sure that you can see that there's a peak here. It's kind of up against here, so that there are actually 1, 2, 3, 4, 5, 6, 7 carbon peaks in this, in that carbon 13 NMR. And then also the last thing, and we've had you do this pretty consistently. So we want to know if you made pure 5-methyl-5-nonanol using a Grignard reaction. Okay, and so you've obviously done some looking up, you have some data, you have some IR, you have some spectra. You want to use that information to write a detailed or good conclusion, and in that conclusion you want to use details from, but not necessarily copy your interpretation of IR and NMR Okay, so you just want to make sure you just include details. The other thing, as always, that you should include is some sort of comment on the percent yield. It was low, it was good, it was high, it was, and then why it was low or good or high. Okay, so that is the lab, the Grignard reaction lab. So have a great day, everybody. If you have any questions, reach out.